Hey everybody. I would like to spend some time talking about Lab 7. I find that many students will struggle with Lab 7 because this is really where we start to jump into heavier computer science topics as they relate to algorithm design and programming design. Um, Sorting, searching, real complex decision making, and so on. And this chapter is pretty heavy actually. We're looking at algorithms that are trickier. They require you to make multiple assumptions, and you have to think through different boundary cases that may apply to your algorithm. This lab takes some time as well, so I'm doing this video a bit early. I find that lab, if the organization of the class was a little bit better suited, you'd have 2 weeks to do lab 7 instead of lab 6. But I would suggest you get going on it earlier, and even work on it while you're working on Lab 6. And so I'm going to do a couple problems that are similar to the problems that are in the lab that hopefully give you a taste of what I'm looking for. So let's do the first one here. So problem example number 1, we're going to talk about March Madness. And for those of you that don't know what March Madness is, it is a 64 team single elimination basketball tournament for college basketball. And don't worry about those like extra pre round of 64 matches that happen. We're not going to worry about that. We're going to go back to just 64 team single elimination basketball tournament. And so the question here is, how many games are played? That's the question that we're gonna try to figure out. We're gonna design an algorithm to answer this question. All right. So when I say design an algorithm, I'm not looking for Python code. I'm not looking for C or C++ code. I'm not looking for, syntax that looks like a programming language. I'm looking for something that is more English but still precise enough. And this can be tricky. And there's a lot of latitude here. So I'm just going to give you an example of what I did here. And so I'm going to say step 1, I'm going to set the value total games to 0. Also in step 1, I'm going to set the number of current teams to 64. You might be saying, okay, why can't I just use total games equals 0 and current teams equals 64 and use Python syntax? The answer here is because I don't want to be talking about a specific programming language here. I want to be putting this in a format that any software engineer or any user experience designer or any product owner can use to take the next steps here. Okay? Step 2. While we have more than 2 teams left, do the following. Step 3. And so I'm going to indent this to show that there's this kind of structure that does exist in the programming language, but indentation is not necessarily needed because I'm going to say do the following, and later I'll say when to stop, right? So step 3 is, we'll say the number of matches, or the number of games for the current round is the current number is current teams divided by 2. Add that value to total games. And then we'll also say step 4, subtract that value from current teams. And so, and that's because half the teams lose, right? Half the teams lose and are eliminated. And then step 5, Actually, there is no step 5. So we'll do step 3 and step 4, and then we'll go back to step 2 effectively, right? So we might want to say, now go back and evaluate step 2. We can be specific if we want, right? Return to step 2. All right. Let's quickly go through this and see if it worked as I tried to do this on the fly. All right. So we start with step 1, and maybe what we'll do is we'll make a table here. All right, and we'll say total games and current teams. So we start with 0 games and 64 teams. Okay. Step 3. We add 32 to the total games, right? We divide 64 by 2, and we add it to 32, and then we also subtract 32. So then we do step 3 again. We divide 32 by 2, and that's 16, and that gets us to 48. And then we say 32 minus 16 equals 16. Step 3 again. Since, remember, we're to keep going when we have more than 2, while we have more than 2 teams. So we have 16 teams here. So now we do 48 plus half of 16, which is 8. And that's 56. 16 minus 8 equals 8. Back to step 3 after we evaluate step 2. 56 plus half of 8 is 4 is equal to 60. 8 minus 4 is equal to 4. Step 3. 60 plus 2 equals 62. 4 minus 2 equals 2. Step 3, 62 plus 1 is equal to 63. 2 minus 1 equals 1. Do we do step 3 again? No. We step 2, we stop. Because we only have one. Well, we should say step 2 should be more than one team. In other words, 2 or more teams. So let's fix that. All right, so there's our example that says that we played 63 games to get this done. Some of you, especially those of you that follow the tournament, will find this very intuitive. You kind of know what happened here. But a simple way for us to convince ourselves that 63 is the right number is that in order for there to be one winner, every other team needed to lose one time. And so 63 teams had to lose. And if 63 teams lost, that means that we're 60. That means that there were 63 teams that lost and 1 win, which means there were 64 games played. Right? And so each team had to lose 1 time. Also, the other way you can think about this is that there were how many rounds? There was 1, 2, 3, 4, 5, 6 rounds, right? And 2 to the 6th power is equal to 64, right? Because we're basically cutting the list in half each time. And so when you deal with powers of 2, this may become, again, more intuitive here. All right, so that's the first example here. And so this is the type of stuff that I'm looking for when I say design an algorithm. And if you need to show your work to show the results, doing a table or something like this is very useful. All right, let's go Let's go ahead and do one more. All right, problem number 2. There's a pretty famous mathematical sequence called the Fibonacci sequence. And some of you are likely familiar with it. But it's basically a sequence where a given number is the sum of the previous 2 numbers in the list. By definition, the first 2 numbers are 1. So here's what our list looks like. It's 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, 21 plus 34 is 55, and so on. There's a lot of trivia around this Fibonacci sequence if you want to read about it. And it's surprising how often it comes up in mathematics and in natural sciences as well. But we're going to write an algorithm to determine the 100th number in the list. Okay? And it could be any. It could be the 200th number or the 1 millionth number or whatever. It really doesn't matter. But in this example, we're going to do the 100th number. And so we'll start by doing some initialization. Let's define the variable, or let's define, I'm not going to use the word variable. I'm just going to say current 1 and current 2 as the 2 most recent numbers in the list. Let's define position as the nth element of the list. Set position to 3. Set current 1 and current 2 each to 1. Okay, so in other words, I'm initializing my list. I'm going to set current 1 to 1, current 2 to 1, and I'm going to set my position to 3. And so we'll say step 3, while position is less than 100. Step 4, set the value total equal to the sum of current 1 and current 2. Step 5, set the value current 1 equal to the value of current 2. Step 6, set the value current 2 equal to the value of total. Okay, so what I did here is I summed up my 2 numbers and my 2 current positions. So I figured out what the next value was. And then I basically moved 1 position over in the list, right? So I shifted things to the left. And then step 7 is increment the value position. So we're going to go through this loop, right? And at this point, we've hit the 100th position, and the amount in total is the amount we care about. And we're done. Okay, so let's go through. I'm not going to do 100 of these because that'll take forever. But let's go through this example, and we'll use a table here. Make this smaller. Okay, this should work. All right, so we'll say current 1, current 2, total, and position. So we start with this equal 1, this equal to 1, and the position equal to 3. Okay, we're going to go through this loop here. We're going to add current 1 to current 2, and we're going to make this equal to 2. And then this value of current 2 will move into current 1. This value will move into here, and we'll increment position to 4. Okay, so we re-enter the loop now, and we're going to calculate the value at position 4, which will be the sum of 1 and 2, which is now 3. And that matches if we look up here. And then again, we set current 1 equal to the value 2. We move that there. We move that there. We increment our position. And we do it again. 2 plus 3 is equal to 5. And we put 3 there. We put 5 there. And we move that up to 6. And so on. And we could do this, another 90 some odd time to get the right answer here. But this is essentially how this works. So again, for problem 7, or lab 7, these are the types of algorithmic work that you're going to want to do. You might want to draw pictures. You might want to write some things out. You, by the way, can always code this thing in Python to check your answer if you want. But please do not submit Python code to me when I say write out an algorithm. As usual, I will post these 2 slides. In this case, they're PowerPoint slides. I'll post these along with a link to the video here. And if you have any questions, please respond in the discussion post. Thanks for watching.